these two will be some integer of h bar. Okay, so this integer can be the non-negative integers. So m can be 0, 1, 2, 3, dot, dot, dot. Alright. But we know that mu b is equal to, well, we know that mu t is minus mu b. So now we've got so minus mu b is just mu t. So now we've got 2 mu t is mh. So mu t is just m over 2 h bar. Right? So we now know what mu t is here and here. So it's m over 2 h bar. So lambda will be of the form L into L plus 1 h bar squared, where L takes the value 0 or a half or 1 or 3 over 2 and so on. So it goes up in multiples of a half each time. Okay, so prove that as well. It's just fairly simple algebra. Right? 12-year-old could do it. Forgetting physics, just simple algebra. Okay, so what it's summarizing a little bit now. So by just using the commutation relations, the square brackets between matrices, 2 by 2 matrices, right? We found the eigenvalue spectrum. Right? So we know what the m's are for mu. Mu is the eigenvalue. Mu takes integer values of h bar here. So we know all possible values of n. Okay? And the eigenvalue lambda, what possible angular momenta can you have? Well, they're also quantized in the form of L into L plus 1. But L now is an integer as before. It now increments in half integer, in multiples of a half for these 2 by 2 matrices, matrix equivalents, matrix representations. Okay, so L can take the value 0, a half, 1, 1 and a half, 2, dot, 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 dot. Right? Okay, so the angular momentum, so L, is quantized. That's down here. Here it is here, in increments of a half. Right, half integral units of h bar. Well, this is the eigenvalue of L squared. Right. Okay. Now, so for the lowest non-trivial case, that's when L's, if L's 0, it's just trivial, right? Your eigenfunction's nothing and it's boring. But for the first non-trivial, the next one up is a half, when L is a half. Okay? And if L's a half, M is plus or minus a half. Well, those 2 by 2 matrices that correspond to L squared and to LZ, you can write down immediately because they're diagonal matrices and the diagonal elements are the eigenvalues. Right? Well, we know the eigenvalues, so bam, you can write down the 2 by 2 matrices for L squared and LZ. And with a bit of work in the commutation relations, you can find what Lx and Ly are. More homework, okay? Right. Now a bit of discussion, asking the question, well, what went wrong? I mean, here we now have quite different eigenvalues, and like L's a half, didn't have that before. It was always integer before. Using the wave functions, the eigenfunctions of the angular momentum operators that were spherical harmonics, right? The y the Y, Lm. So using spherical harmonics, we didn't get these half integers. So these 2 by 2 matrix representatives are the representatives of what actually? This seems to be a different kind of angular momentum, right? And if you go way back to the beginnings of our analysis on angular momentum, quantum mechanical angular momentum, remember we started with the correspondence principle, and we took our analogy from the classical mechanical definition of angular momentum. The little wiggle under here means it's a vector. And angular momentum in classical mechanics is defined as the position vector cross product momentum vector. So all our integral values of L and M came out of this. So could it be that with this case now of 2 by 2 matrix representations, is it that matrix representation, is it representing some kind of angular momentum that does not take this form? Because this is classical, right? And I'm asking a rhetorical question, obviously. I'm leading into the idea that there's something new here. There's some kind of so-called angular momentum that is not of this classical angular momentum form, yet its quantum mechanics obeys the same kind of commutation relations as the quantum mechanics that was derived from this. So this new kind of angular momentum, which the 2 by 2 matrices, or 4 by 4 or 6 by 6, the even-sized matrix representations, they are representations of what? What operators? Well, we're heading towards a new kind, of angular momentum, and it will be called spin. And it's a kind of intrinsic angular momentum, and it has no classical mechanical equivalent. It's something uniquely quantum mechanical, and we're just scratching the surface now, and we can take this concept of spin right up, let's see how far, right the way up, another 4 layers above this undergrad level. Take it through quantum field theory, certainly, so Masters 2 level, PhD 1 level, even Witten's stuff uses it. So we'll take it right through. So this concept of spin is very, very important.